Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. In this module we will begin with a few applications of Smith chart, the use of Smith chart to solve transmission line problems. We will continue this in the next few modules, and what I would suggest, as I suggested in the previous module, is that you have a Smith chart access, you either have a Smith chart printed or downloaded copy with you, and while I sketch the points and solve the problem, you try to replicate the same thing when you are actually when you are viewing the video lectures. So that way you will be able to understand how to use Smith chart to solve the problems that we are going to discuss. So we begin with basic use of Smith chart we have already discussed. So what we will now do is to see what type of problems that Smith chart allows us to solve. So one of the typical application of Smith chart, very basic application of Smith chart, if you would think, is to find the impedance, right, of a load that is connected to the transmission line, but at the position away from the load. So what we are trying to find out is the line impedance, the impedance measured on the transmission line at any point on the transmission line, given that load is ZL. Okay. So remember how to solve this problem. You can solve this problem without using Smith chart, because given the value of ZL and the corresponding Z0 of the transmission line, if these two quantities are given to you at any point on the transmission line, you can use this impedance transforming formula that we discussed in one of the previous modules and find out what would be the impedance at that particular point on the transmission line. So the line impedance can be easily found out by transforming the impedance ZL through the distance at which you are seeking the impedance. So if I were to sketch the problem for us, the problem that we are trying to address is that I have a transmission line, okay, and to this transmission line we have connected a load, and we give you the value of the load ZL. This is of course at a particular frequency that we are considering, and the transmission line itself has the characteristic impedance of Z0. In all of the applications that we are going to consider, we will assume that this Z0 to be a real quantity. Okay. So which means that the characteristic impedance of the transmission line is purely real, the line is completely lossless. Okay. At any point on the transmission line I can find out what would be the impedance, right. So how do I find out what is the impedance? We will call this as input impedance, although this is not really input here, it is just the line impedance that we are calling. So this impedance seen at any point Z on the transmission line can be obtained by some complicated formula. It is reasonably complicated that I do not normally remember that one unless I start deriving that, but I know that this complicated formula expects us to provide with ZL, which is the load impedance at which the transmission line is terminated, the characteristic impedance Z0, as well as the point at which you are trying to find the impedance. Okay. If you know all this, and of course the wavelength lambda, remember that on the transmission line problems all lengths are normalized with respect to wavelength, right. So given these 4 parameters, you will be able to find out the impedance. Okay. However, if instead of asking you the impedance at this point, if I ask you for the impedance at this other point, you will have to use this complicated formula which will have sine, cos or tan equivalently and recalculate it. So this is where Smith chart will help you. It will provide you with a graphical way of solving this same problem. You do not have to use a calculator. All that you need to do is to have a Smith chart with you, a pencil or a pen depending on what you are using, a scale, a protractor, a compass. These are all the things, that geometrical things that are needed in order to solve this problem geometrically. So that is why we call Smith chart as a graphical aid. Okay. It provides you with a graphical or with a geometrical way of visualization of the transmission line problems. So how does Smith chart help in this scenario? Let me erase all this complicated formula thing and tell you how easy it is to use Smith chart in order to find input impedance or the line impedance at any point. Okay. Of course, you still need to know what is ZL, you need to know what is Z0, lambda you need to know, and the distance at which you are trying to find the impedance you need to know. So all these quantities are needed. But on the Smith chart we have a very interesting way of finding this, very interesting and a very simple way of finding the impedance. So first we start with the Smith chart itself, okay, and I will draw only a few circles and a few representative arcs. So this is just not to clutter up the entire Smith chart, but in your possession you will have a Smith chart with you, so you can be more accurate. I will be slightly inaccurate. My goal is to try and show you the methods, okay, not to give you the exact value. That exact value can be obtained once you have the Smith chart with you, okay. So this is the Smith chart. Please remember what is Smith chart. Smith chart at any point is just a correspondence between the reflection coefficient gamma and the normalized impedance Z bar, right. So it is the reflection coefficient and the normalized impedance Z bar, which is what is actually plotted on that Smith chart, right. I have already talked to you about the constant R circles, constant X arcs, and any point on the transmission, I mean on the Smith chart will simultaneously represent gamma, which is the reflection coefficient, as well as the normalized impedance. And since it is normalized impedance that we need to talk about, we need to normalize every impedance that we come across in the transmission line problems. So what is the normalization value, or to which value should we normalize? It is to the characteristic impedance of the transmission line to which we need to normalize. So the first step, if you were to start off, step A, okay, would be to normalize the load impedance which is given with Z0 and obtain the normalized load impedance ZL bar, okay. On the Smith chart I can easily locate where ZL bar is, because ZL bar will be in some R plus Jx way. If it is inductive reactance that the load possesses, then this X will be positive and all those values will be in the upper hemisphere. If X is negative, it indicates capacitive reactance, in which case these R plus Jx values will be found in the lower hemisphere, which we have already seen in the earlier module. So how do I locate this ZL bar? Well, I need to find out the corresponding R and a corresponding X. For this application, let me just consider R equal to 1, X equal to 1, okay. So this clearly lies in the above or the upper hemisphere part. So I locate R equal to 1 circle, which is this circle, right, and then this is X equal to 1 arc or X equal to 1 circle. Therefore the point that I am looking at happens to be here. Let me try and use a different color to this point. So this is the point at which we have the normalized load impedance. But please remember, whatever that you find as the load impedance, at this same point you can also specify the reflection coefficient. How? Because the axis that you have here is actually the real part of the reflection coefficient gamma R, and this axis y is the imaginary part of the reflection coefficient. So clearly whatever the point that we have labeled here, let us call that point as point A, okay. At this point A, if I were to make a line from the center, let us call the center as O, okay, center of the chart as O, and if I now draw a line OA connecting O to A, the length of this line will tell me the magnitude of the reflection coefficient at that particular point. Since we are just starting with the load here, so this is going to give me magnitude of the reflection coefficient, okay. We also have seen that the largest circle on the Smith chart will have the maximum value of gamma L, correct, and that maximum value will be equal to 1. So for example, if I am located on the outer periphery of the chart and then draw this line will have the maximum value of gamma L, which we will have to take it as 1. Of course, if I were to actually print this chart on a piece of paper, this will be some number, that is 0, and let us call this as some m, okay. OM might be 3 centimeter for example, it may not be, I am just giving you an example of 3 centimeter, okay. In which case the magnitude gamma L at A can be found out by the ratio OA divided by OM, right. This is the largest magnitude that you are able to find, which will have a gamma L of 1. Therefore, this line OA must be proportionately scaled up by this OM value. So, normalize it, and then what you find, the ratio of OA to OM will be magnitude gamma L. Okay. But this is just the magnitude of gamma L. You can also find out the angle from the real axis and find what is the corresponding value of phi L. So, effectively point A has represented the normalized load impedance. It also has represented or given you load reflection coefficient gamma L. These values are known at the load, but let us say I want to find what would be the impedance at this particular plane, which happens to be some distance L away from the load. Okay. So, at some distance L away from the load. Now, remember what is the reflection coefficient magnitude behavior. The magnitude of the reflection coefficient as you move away from the load towards the generator or towards the source will remain the same. Magnitude of gamma L will remain the same as you move from load towards the generator. So, as you move towards the generator, the magnitude of gamma L will remain same. But if you have travelled a certain distance L, then the phase of this reflection coefficient angle will have changed by a value of 2 beta into L, and of course this has to happen in the clockwise direction as we have seen. So, there is one possible way of finding the new value of the reflection coefficient at this particular plane. You can find out the new value of reflection coefficient, which is complex reflection coefficient. Let us call this as just gamma, not gamma L, because you have moved away from the load. From this gamma you can find out the impedance, normalized impedance. From the normalized impedance you can find out what is the input or the impedance, line impedance at that particular point. So, you can do this mathematically, right, once you have done the graphical thing, or since every impedance that matters is already present in the Smith chart, you do not have to do any of these things. Okay. After you have located the load, okay, move a distance of 2 beta L or move an angle of 2 beta L clockwise direction. For this you can either put your protractor and then measure the angle phi L, and then from phi L subtract 2 beta L and then locate on this circle, locate the new value of the reflection coefficient. At that point find out what would be the angle, right. So, if I were to follow that method, first I have to draw a circle, right. This circle along which gamma L will be constant will be called as constant gamma L circle, but I also know that constant magnitude of gamma L will also help me calculate the value of the standing wave ratio, and standing wave ratio would also be constant. Okay. So, this circle therefore is called as constant SWR circle. Here this circle has a certain radius, and we will come back to finding the exact SWR value later on, but this is called as the constant SWR circle. So, on this circle you need to move clockwise. You see I moved here all the way. So, maybe I wanted to stop at this point because that would have given me 2 beta L movement. I obtain on this circle a new point. So, I start from 0, then center this, I mean with the 0 as a center, and this new point which we will call as point B, I draw the line, and at this point I read out what is the value of R and X. In this case it turns out to be, I mean very close to the value of R that you are looking at is about 1, and then X will be about some value which would be less than 1. But please do not go by the exact number that I am writing here, because that is not the correct value that I have obtained. This is just the procedure that I wanted to tell you. Let me do one thing. Let me first erase all this and tell you what exactly the procedure that we have followed. So, this was cluttering the entire discussion. So, we do not need to clutter ourselves anymore. So, let me solve the problem for you in a simpler way, or rather give you the procedure. Remember what we wanted to find out was that we wanted to find out what is the impedance at a certain distance L. So, the method that we started was start with ZL bar, okay, on the Smith chart. Okay. So, I will use the word SC to denote Smith chart. Okay. So, on the chart you mark this one, this happens to be the point A. Okay, on the chart this happens to be the point A. With OA as radius, draw the constant SWR circle, which is this black circle. So you can see this black circle that I have drawn, that corresponds to the constant SWR circle. Then determine how much you have to move. You have to move an angle of 2 beta L. How do you find out beta? Beta is already given to you. So 2 into 2 pi by lambda into L. Please note that this is in radians. If you want, you can convert this radian value in degrees as well. So in which case you will be moving 2 into 360 degrees into L by lambda. So it's just the way of whether you measure things in radians or degrees that matters. Okay. So you are moving 2 into 2 pi by lambda into L radians along clockwise. So you have to move along the constant SWR circle clockwise direction, okay, to locate to new point. So at point B, read the corresponding complex impedance. This will give you only the normalized complex impedance. Multiply, this is the final step, I will write it here. Multiply Z bar by Z naught in order to obtain the unnormalized impedance at the distance L away from the load. So this is a very simple 5-step procedure maybe. Okay, we can even simplify this procedure further. I will tell you how to do that. Okay, so let us solve the same problem that we solved earlier. So we again begin with a simple Smith chart, not trying to clutter your Smith chart for you. So I will draw just a few arcs as I did in the previous page, and I will draw a few important circles. That should be all. Okay. The first step is to again locate r equal to 1 and j equal to 1. In this case, this happens to be the point here, which is the point A. This is the load point. A is the normalized load value with center O and OA as the radius. I draw the constant SWR circle. So I have completed step A, I have completed step B. Now what I do is I extend this line A outside the chart. Okay. If you examine your Smith chart closely or follow the last module, you will see that there are two scales printed on the Smith chart. One scale is called as WTG scale. It says wavelengths towards generator. Okay, this is the way in which you move away from the load and towards the generator. So on that WTG scale, note the point A prime. Okay, so note down the value of A prime. So let us say A prime happens to be something like 0.15 lambda. Okay, this is not the actual value. So please, again I am cautioning you, this is not the actual value. You note down whatever is the WTG scale value. By the way, this value will simply be used as a reference. It has no meaning whatsoever that it is required. Okay. Next, what you need to do is, you know what is the value of L, that is at what distance away from the load you are trying to find out, at what distance away from the load you are trying to find out the impedance. So you divide that L by lambda. So let us say after you have divided L by lambda, it turns out to be 0.2. Okay, or in terms of L itself is 0.2 into lambda. Okay, what you need to do is that from the WTG scale that you have noted at point A prime, which happened to be 0.15 lambda, add 0.15 to 0.2. Okay, this will give you 0.35 lambda. So on the WTG scale, you keep moving. Okay, and you land up somewhere over here. So this is 0.25. If you look at the Smith chart, this would be like this. So this is 0.125, this is 0.25, this would be 0.375 and so on. So 0.35 should come somewhere over here. So let us cut this. On this WTG scale, I have moved a 0.2 lambda, which is I have actually landed on 0.35 lambda value. So this scale is continuously marked in the increasing value of 0. Okay. So clearly whatever is 0.25 will also be the same as 0.5 here. Sorry, whatever is the 0, that would be the same as 0.5. Okay, and 0.5 corresponds to lambda by 2, which is one complete rotation. So you go from A, extend the line to A prime, find out the value. That value is just for the reference that we have found. used. So from that to that value you add 0.2, which is the distance that you have to actually move normalized with respect to lambda. So you need to add 0.2 lambda to come up to 0.35 lambda on the WTG scale. Once you have obtained that point, call that as B prime. Now draw a straight line from O all the way to B prime. Okay. Now you see where you are intersecting the SWR circle, you are intersecting the SWR circle here. Call this point as point B and read the coordinates at B. Multiply that coordinates by Z0 in order to obtain the impedance at a distance of L away from this. So I hope you really appreciate the simplicity, although I have taken about 20 minutes to explain the concept. I did this so that you really understand what is going on with this simple application. Once you understand this application, other applications are quite easy to follow. Okay. So let us consider a second application of Smith chart. Okay. In this application we are trying to find out the value of the location of the voltage maxima and the location of voltage minima on the line, right, voltage maxima and voltage minima on the transmission line. Why should we have voltage maxima and minima? Whenever you have terminated a transmission line, which is this line, with a load which is different than the characteristic impedance of the transmission line, you will see that there will be a voltage maxima minima pattern. So this will be the standing wave, voltage standing wave pattern. This is not VSWR, but this is just the voltage standing wave pattern, and you would see a series of voltage maxima. So this is V max and this is V min. Okay. So depending on the load you will have the locations of V max and V min to be different. Okay. How do I find out when we will hit the voltage maxima and the voltage minima on the line? Well, it is kind of very simple, right. Let us start again by the Smith chart. Okay. So this is the Smith chart, right, and then assume that we have been given a certain load impedance. Okay. So we have been given a certain load impedance to work with. So this is the Smith chart. As before, if ZL is given, find out what is ZL bar. ZL bar is clearly ZL by Z0. We will again go to some arbitrary location. So let us say this is the value of ZL bar. Okay. This is 0, this is A, and I need to draw a constant SWR circle. So this is usually the first step. So okay. So you draw the constant SWR circle like this. Now imagine that you keep moving along this constant SWR circle shown by this arrow towards the generator, right. So you keep moving and you reach this point, okay, this red point on the horizontal axis, you reach that point. If I now ask you what is the value of gamma L here, you will tell me the value very easily, because the value of gamma L magnitude is simply given by this length, right. So I have reached a point, let us call this as point P. Okay. So OP divided by OM, please remember what is OM, OM is from the previous application, right. So OP by OM will give me the magnitude of gamma L, but at this point what is the phase angle of gamma L, or rather I should not call this as gamma L, I should simply call it as, well, it does not matter, it would be gamma, but the magnitude anyway does not change, so I can call it as mod gamma or mod gamma L, does not matter. So you actually what you have done is you have started off at some point, okay, at maybe at this point, and then as you move towards the load you have now reached this point V max. Why? Because the phase angle here will be equal to 0, right. So if the phase angle is 0, what would that indicate to you? So what is the voltage at that particular point? The voltage along the line at the point where phi L is equal to 0 is simply given by magnitude. So since you are only looking at the magnitude, this would be magnitude of V0 plus into 1 plus magnitude of gamma L, correct, because this would be 1 plus gamma L magnitude into e to the power of phi L, or e to the power of j 2 beta z plus phi L, and then as you have moved a certain distance z equal to some z max, at that particular point the total phase, this is the total phase which would be the load phase angle plus 2 beta z, this entire thing is equal to 0, right. Since this entire thing is equal to 0, gamma there will be completely real. and this would be the maximum value of the voltage that you are going to get. And how much distance you had to move here. So this will give you the location of the voltage maxima, and how much distance you had to move will give you the location of the voltage maxima from the load point, right. So you moved this particular distance. As usual, I mean as before, you go and find out what is A prime on the WTG scale. This is 0.25. Suppose you found out that this was 0.15, then clearly you must have moved 0.02 lambda in order to land up at 0.25, right. So you had to move 0.02. Therefore, from the load, the position of load maxima happens at 0.05 lambda. This is not the only position. On a lossless transmission line, you will again find the maxima at 0.05 plus lambda by 2, right. So, 0.05 lambda plus lambda by 2 or 0.55 lambda, because every lambda by 2 these positions will keep changing. So, this is how you find out the position of maxima. Now, a very interesting thing has happened over here. You have found out what is the line impedance, and you have found out what is the corresponding value of this location of the load maxima. You can use the value of magnitude gamma L to also find out what is the maximum value of the voltage, provided of course someone has given this V0 plus to you. Okay. If someone specifies what is V0 plus to you, you will be able to find out what exactly is the voltage maxima. At this point, I have another interesting bit for you to find. Okay. Let us look at this point, right. On the horizontal axis, starting from the point A, we landed at point P, right, on the horizontal axis. What would be the normalized impedance value there? So, at this point, we also have one more interesting information. In order to find out that information, let us look at what is point P representing. So, at point P, we have the voltage to be maximum, but we also know that the current there will be minimum, correct. So, what is the ratio of the voltage maximum to current minimum? That would be the maximum value of the impedance, and at this point both quantities Vmax and Imin are real quantities. Therefore, what you find is the real maximum value of the impedance. So, the maximum impedance that you can find, or the maximum resistance that you can find on the transmission line, will be equal to R max, and this fellow will be equal to Vmax by Imin. The ratio of these two will be that. And what is Vmax? V0 plus magnitude into 1 plus mod gamma L. And what is Imin? Imin is V0 plus magnitude but divided by Z0, because this is the current, and 1 minus magnitude of gamma L, correct. So, now R max is equal to Z0 into the quantity, which is 1 plus mod gamma L divided by 1 minus mod gamma L. This quantity is nothing but standing wave ratio, and you can now see that if I divide this R max by Z0, which will give me the normalized impedance R max, that would be equal to SWR directly. So, what I find at P are two different values. One, I find out what is the normalized maximum impedance or resistance on the transmission line, that is R max. I will also find out the corresponding value of SWR. In fact, at this point, if you read out whatever the value that is there, here it might be about 2.2 or something. Okay, the 2.2 will simultaneously give you the standing wave ratio and also the normalized maximum resistance. If you then multiply this normalized maximum resistance by the characteristic impedance of the transmission line, you will be able to find out what is the value of R max. Now, there is another thing that you can find out from this, right. So, let us continue moving along the same circle. Okay. As we continue to move along the same circle, after a length of lambda by 4, sorry, after a distance of lambda by 4, I land up at the point Q. At point Q, the voltage maxima which was there must be converted to voltage minima, right. So, I convert this one into voltage minima, and when the voltage is going through the minima, the current will be going through the maxima. So, what we find at point Q are the normalized value of the minimum resistance that you are able to find on the transmission line and 1 by SWR. I will leave this as simple exercises for you. you just have to invert this relationship and then find out that this would indeed give you R minimum and 1 by SWR. So, we have actually covered two applications here. One is we can find out the location of the voltage maxima, and also this particular locations happens to be the voltage minima as well, because the phase angle here will be 180 degrees, right. So, with respect to the x axis, the phase angle will be equal to 180 degrees, and at that particular point gamma L or gamma becomes minus magnitude of gamma L, and then what you get is the voltage minima. And what is the location of the voltage minima? Starting from A prime, you have moved a certain distance here on the WTG scale, right, or you already know how much you have moved to find out V max. Add to that lambda by 4 and you will be finding out what is the location of the voltage minima, as again the voltage minima keeps repeating every lambda by 2, okay, traversing thing. So, at point Q you found out the minimum value of the resistance, you found out what is 1 by SWR, okay, and you can also, and you have also found out what is the minimum value of V min. So, you know what is 1 minus mod gamma L, you can calculate that one, and if you know what is V0 plus magnitude, you can easily find out what is V min, okay. In fact, knowing the V max and V min values allows you to construct the voltage standing wave pattern. It will allow you to, once you know what is V max and V min, it will allow you to construct this particular graph, okay. So, that is one other application in case you are interested, how to find out the standing wave pattern on the transmission line, how to sketch that one. So, you need to know the location of the maxima, location of the minima, what is the value of the V max, what is the value of V min. So, all this information can be very easily extracted from the Smith chart. Thank you very much.